All right, once again, your standard. This is called a circular pendulum, and we're going to go ahead and actually draw the free body diagram. I'm going to change my perspective, though. I'm going to kind of draw the pendulum, redraw the illustration like this, just so I can make some sense of it. And then there's the centripetal acceleration towards the center here, and it moves in a circle. So the other thing I want to do is, we're told that this radius is r, so let's just be clear that this length here is L squared minus R squared under a square root, which makes things super exciting as far as the trig goes. So I have this angle theta here, and when I actually do that, let me color code some things here. So this length here is L squared minus R squared. This angle's theta. And look at all this delicious trig. We have that the sine of theta is gross L squared minus R squared over L. Yuck. And a cosine theta is R over L. Ew. Okay, so that's the trig. I think it's kind of neat, but I have empathy for my students. So let's draw a free body diagram of the Bob. This is the Bob. Bob, it's such a great minion name. All right, so we have this tension here, and we have the weight of the Bob due to the Earth. And now we can actually add our little force components. So we have here, oh, look at that, T cosine theta and T sine theta. All right. Now, do we have any friction? No friction, thank goodness. This problem with friction would be kind of tricky. Because if friction actually acted like air resistance or something, you need an air resistance term, and this would no longer be a circle, it would actually be spiraling towards the center, and there'd be a very complicated equation for that. And you are free to do that when you take your third year of physics, because you're going to be doing freshman physics, which is a repeat of this stuff, but in more in depth. And then you'll be taking an advanced mechanics class where you will actually be using oh, and then this is a dissipative force, which makes it so interesting. I'll let you worry about that in the future. So this angle's theta. And now let's go ahead and set up our equations in x and y because we don't have friction. And we want the tension in the string and the period of the motion. What we mean by the period is the time for one orbit. Okay? And by the way, the letter we use for that is also capital T, but we won't worry about that for now. We'll just use lowercase t. So here we go. In the y direction and in the x direction, we've got our equations. So in the x direction, we do not balance. We get circular acceleration. So we actually end up getting t cosine theta equals m times acceleration. And in this case, that's t times r over L equals the mass, m times v squared over r. And let's just see where this goes. Okay, and then in the y direction, they do balance. So we end up getting t sine theta minus the weight equals 0. And this actually works out to t squared, t times the square root of L squared minus R squared over L balances the weight. Now let's look a little carefully and see what we can do for numbers. So one of the nice things is they say the circumference is 0.94 meters. Are you kidding me? Okay, I'm going to pick a color of ink that expresses my mood about this ridiculous piece of data. Okay, there, we'll pick asparagus, which to me honestly looks like doggy-doo. So that is my opinion of this way of presenting the information, because circumference is 2 pi r, and I just want r, so we got 0.94 equals 2 times, let's just be lazy and use 3.14. I know some of you have pi memorized out to like 900 digits. That's cool, okay, but it's not that cool. Okay, it's pretty cool. All right, so let's get that radius. Get that radius! Okay, 0.94 divided by 6.28. That gives me 0.15. 0.15 meters. Look at that. That's our radius. That's our story. We're sticking to it. So I'm going to use that here. And did they give me L? L is 0.9 meters. Sweet. All right. So there we go. I have T times 0.15 divided by 0.9 is, M is 0.04 times V squared divided by 0.15. And let's see. We also have the tension times, here we go, 0.9 squared minus 0.15 squared under a square root divided by 0.9 is m times g. That's going to be 0.04. That's going to be 10. So I'm going to get 0.4 here. Great. So here's what I'm going to do. I can actually solve for the tension first. And then I'll plug it into here. Equation number 2. So let me go ahead and get the tension. So this tension is going to end up being 0.4 times 0.9, all under the square root of 0.9 squared minus 0.4 squared. This part of talking, by the way, when I'm like writing down numbers and just reading them out too, it feels like I'm like watching paint dry. I hope you're having a similar fun experience. So 0.9 squared minus 0.4 squared equals 0.65. We'll square root that. Okay, and then 1 over times. So I got a tension of 0.44 newtons. Meow. Pretty exciting. All right, now what can I do with that? Now this is the result for number 1, right? So I'll just move this here. So this is the result for number 1. And then I'm going to take result number 1 and plug it into number 2. And we're going to end up getting here 0.44 times 0.15 divided by 0.9. I need to bring the other 0.15 to this side, and I'm going to divide by 0.04, and that's going to give me V squared. So there is some arithmetic I could do to simplify this, but I'm actually not going to. So 0.44 times 0.15 squared equals divided by 0.9 times divided by. So I'm here getting a speed of, so I got V is equal to 0.52 meters per second. If you've got 0.54, 0.51, or 0.53, you're fine. So that's what I got for the speed. And this is what I got for the tension. And looks like that is question number 4.